Thank you very much. So this is a joint work with Michel Rabitsky, and it concerns symplectic embeddings of balls into closed symplectic manifolds. So let me first introduce the setting. So we have a closed symplectic manifold M with a symplectic form omega, and B of R will be always a closed ball of radius R centered at 0. So by an embedding of a closed ball, I mean an embedding of its open neighbor. Right? Whenever I'm talking about smooth embeddings, symplectic embeddings, or whatever, these are embeddings of open neighborhoods of closed balls. Okay, and these embeddings have been studied for a long time, since the early days of symplectic topology, but most of the results so far concern the existence of such embeddings, and very little is known about the topological properties of such of the space of such embeddings, or little is known about the action of symplectomorphisms on the space of such embeddings, and so on. So the motivating question here is that assume that you have two symplectic embeddings of a collection of balls, the same collection of balls. Can they be mapped into each other by the group of symplectic isotopies? In this case, this is the same as by Hamiltonian isotopies, or by just any symplectomorphism, or by some intermediate groups of symplectomorphisms, for instance, symplectomorphisms acting trivial homology. So this is the motivating question for the study, and very little is known about this in dimension higher than 4. In dimension 4, there is a classical result of McDuff. Previous partial results were due to McDuff, Lalonde, and Dran, and it says that if we have a 4-dimensional closed symplectic manifold, which has, let's say, roughly enough non-trivial Gromov-Witten invariants, for instance, if it is a CP2 or a blow-up of CP2 or a CP1 cross a surface, a symplectic direct product, and then the space of symplectic embeddings of any collection of balls is connected, provided it is non-empty, of course. And the connectedness in this case is the same as just saying that they all lie in the same orbit of the action of simp naught. This is just the standard isotopy extension theorem, which says that isotopy between symplectic embeddings is the same as of balls, is the same as being able to map one of them into the other by symplectic isotopy, by an ambient symplectic isotopy. Okay, but this class of manifolds, for instance, does not include Tori T4. It does not include T4 with any symplectic form. It does not include K3. So there, the question is still open. Okay, and so what we were trying to do here is to say something about this question for other M, particularly in higher dimensional case. And we failed. We can't say anything about the space of all symplectic embeddings. So what happens is that we are going to consider a more restrictive class of symplectic embeddings, where we can use additional tools coming from complex geometry. So that's the idea of this work. So we'll consider embeddings that are not just symplectic, but more than that, and this will allow us to use additional tools that are not available for general symplectic. Okay, so let me give a very brief review of the notions from Kähler geometry that I'm going to use. So we start again with the closed connected oriented manifold of real dimension to n. And from a symplectic point of view, from the point of view of symplectic geometry, what is the Kähler structure on such a manifold? It's just a pair omega j, where omega is symplectic form and j is an integrable complex structure on M compatible with omega. Okay, so that's how we view Kähler manifolds, just pairs omega and j. Of course, together, these omega and j define what is known as a Kähler metric. And a symplectic form or complex structure on M is said to be of Kähler-type if it appears in some Kähler structure. So omega is of Kähler-type if I can find some integrable j compatible with omega. And j is of Kähler-type if I can find some first of all, J is integrable, and then I can find some omega compatible with J. So these are called Kähler-type complex structures and symplectic forms. And further on, I'm going to consider only Kähler-type symplectic forms and only Kähler-type complex structures. In any case, I'll say it again and again, but just to avoid the confusion from the beginning, there will be no symplectic forms or complex structures other than this. Okay, and I always assume that they're compatible with orientation whenever this is a question. Okay, so a few more annotations to be introduced. So simp H is the group of symplectomorphisms of M acting trivially on homology. C of M will be the space of all Kähler-type complex structures on M. And inside the simp of M lives the space of integrable complex structures compatible with omega. So CM omega is the space of Kähler-type complex structures compatible with omega. Okay, so a few more notions from complex geometry. So I look at the space of all Kähler-type complex structures on M, and I mod it out by diff naught, and that's what you get is what is called a Teichmüller space of Kähler-type complex structures on M. And there's of course a natural projection from the complex structures to the quotient space. And then by I in the square brackets, I'll denote just the projection of phi to the Teichmüller space, or in other words, just the diff naught orbit of phi. So I in the square brackets, just the diff naught orbit of phi. Okay, now we are coming to the definition of the symplectic embeddings of balls that we're going to consider. And let me start with just fixing. I fix omega on M. Omega is fixed. Now, this is very important to remember that in our story, the symplectic form is fixed. And what varies is the complex structure. That's the point of view opposite to the point of view of, say, Kähler geometry. When you fix, in general, you fix a complex structure, and then you vary symplectic form, you consider various Kähler forms on the same complex manifold. Here it's the opposite. Symplectic form is fixed. We are going to vary complex structures. So we start with some symplectic embedding, okay, denoted by F. Now, first, let us fix a complex structure J compatible with omega. So in this case, omega and J together define a Kähler structure. We have fixed a Kähler structure on them. That's the first situation. So in this case, such a symplectic embedding is called Kähler or Kähler isometric if it respects both structures, both the symplectic one and the complex one. So it means that it's both symplectic with respect to omega and holomorphic with respect to J. So such embeddings are called Kähler or Kähler isometric, and clearly for such a Kähler isometric embedding, the Kähler metric on the target is flat on the image of the embedding. So that gives you an immediate, very strong obstruction to the existence of such embeddings. Kähler metrics usually have curvature, non-zero curvature. Any point with such a curvature kills the possibility of embedding your balls, say, with the center at this point. So these are not the embeddings we are going to work with. It's been well known for ages that such embedding, such Kähler isometric embeddings is too rigid of an object to study. But we are going to do the following. We are not going to fix J. We only fix omega, and do not assume that any J is fixed in advance. Then, in such a situation, so omega is fixed, but J is not, we say that F, this embedding, is of Kähler type, if in addition to being symplectic with respect to omega, it is also holomorphic with respect to some, not a priori fixed, integrable complex structure J compatible with omega. So, as we'll see, we'll say it several times. So this means that if I take this particular J that I found together with my omega and the resulting Kähler metric, F will be Kähler isometric with respect to that Kähler metric. So with omega fixed, I'm able to find J such that for the resulting Kähler metric, my embedding is Kähler isometric. Okay. So if this J can be chosen to lie in the diff naught orbit of some other complex structure I compatible with omega, then we say that F is of I Kähler-type. So it means that I'm not able only to find J compatible with omega with respect to which my embedding is holomorphic. I'm also able to pick this J from the diff knot orbit of a particular complex structure compatible with omega. And that's what's called I Kähler-type. Okay. So in principle, this J can be picked from many parts of the space CM omega, right? So if such J can be picked from a certain subset of C of M or C of M omega and so on, we'll just say that F favors that subset. That's just for language convenience. When we say that F favors some complex structure or some set, that means that F is holomorphic with respect to that complex structure, from respect to some complex structure from that set. Okay, that's the terminology. And let me make a few remarks about this terminology. So first remark is just a tautology. So what does it mean that F is of Kähler-type? It means that it is of I Kähler-type for some complex structure compatible with omega. That's the tautology. Okay, just a second. Okay, so that's the first remark. The second remark is that, well, in the story that I've just told, we fix omega and let the complex structure vary. Suppose we want to do the opposite. We fix the complex structure and then the omega vary in this pair. So then what we get immediately by using Moser's result is that the existence of I Kähler-type symplectic embedding into omega is the same, and I'll fix I and let omega vary, is the same as the existence of a Kähler embedding into M omega prime for some other Kähler form omega prime on the same complex manifold M I fixed I in the same homology class. If you want to fix a complex manifold in various symplectic forms, then in these terms, the existence of an I Kähler-type symplectic embedding into for a particular Kähler form is the same as the existence of Kähler embedding for another Kähler form, which is homologous to the given one. Okay, that's when you just switch hands and fix I instead of omega. Okay, and for a fixed I, if you take this point of view that you want to fix I and vary omega, this is the problem that was already studied in recent, but in previous, but rather recent works. So for fixed I, the existence of such I Kähler-type embeddings in a different language was previously studied by Eckel, Wittnystrom, Fleming, Luf and Wang, and Torsiani in the last, say, 10 years. Okay. That was the second remark. The third remark is that in principle, a Kähler-type embedding, as I said, may be of I Kähler-type for different non-isotopic I's and may favor several different connected components of the space of all Kähler-type complex structures or just the ones that are compatible with omega. So again, so when you have a Kähler-type embedding, it is symplectic with respect to the given symplectic form, but maybe holomorphic with respect to many integrable complex structures compatible with that form. So that complex structure does not have to be unique. Therefore, a particular embedding may favor different connected components of this sets. Okay, that's remark number 3. Remark number 4 is that, as we'll see later, towards the end of the talk, there do exist symplectic embeddings that are not Kähler-type. So we do have examples for particular manifolds and particular forms of symplectic embeddings for which we can guarantee that they are not of Kähler-type. Okay, but just for a second, going back to remark number 3 is I would like to say that this connected components of the space is something very hard to get a grip on. For a general symplectic manifold, it's extremely difficult. So our applications for particular manifolds will concern only those rare manifolds for which the spaces are well known and well understood, or more precisely, the corresponding type mirror spaces are well known and understood. by previous work of complex geometers. So you just give me an arbitrary symplectic manifold admitting Kähler structures, then I probably won't be able to say anything about the existence of Kähler-type embeddings or whatever. Okay, so these were the remarks, and as you remember, our original goal was to say something about connectedness of the space of embeddings. So made the concession already, gave up on studying all symplectic embeddings. We're studying now more restrictive class, the Kähler-type embeddings. You want to understand whether the space of such Kähler-type embeddings is connected. And then we have to calibrate our expectations appropriately. As you'll see, life is not going to be simple. The picture is not going to be simple. So let me make a few remarks about this. So first of all, assume that you are in the ideal situation. You know that two Kähler-type symplectic embeddings, f and f prime, can be connected by a smooth path in the space of the Kähler-type embeddings. Okay, so assume you've proved your dream theorem that you have two such embeddings. Then by the isotope extension theorem, it's just the same as to say that they lie in the same symptom orbit. Okay, but then this implies that both embeddings are holomorphic with respect to complex structures compatible with omega and lying in the same symptom orbit. Because if you act by symplectomorphism on F, then the symplectomorphism maps the complex structure with respect to which F is holomorphic into a complex structure with respect to which F prime is holomorphic. And if the original complex structure was compatible with omega, the new one will be also compatible with omega because we are acting by symplectomorphism. Therefore, if you have such F and F prime, they have to be holomorphic with respect to complex structures compatible with omega and lying in the same symptom orbit. This is a very strong restriction. In particular, if you want to say something, this immediately produces weaker restrictions, which are also very strong. So they have to be holomorphic with respect to complex structures compatible with omega and lying in the same path-connected component of the space Cm omega, and hence in the same connected component of C of M. And a priori, you have no control about it. You have no control whether your embedding, if you have two Kähler-type embeddings, you have no control whether they favor a common connected component of C of M. Okay, so that's the restriction that you have to deal with. If you have F and F prime lying in the same connected component, they have to favor the same path connected component of Cm omega. And in general, we have very little information of these symptom orbits. If you go back to the original restriction, respect to this one, that they lie in the same symptom orbit, and then we have in general very little information about symptom orbits of complex structures. Right. However, in some cases, we have a better info on diff-knot orbits of complex structures. We are going to consider only diff-knot orbits of complex structures compatible with omega. Okay, and this will lead to results about simp intersection with diff-knot action on the space of Kähler-type embeddings. So we already already announcing here that we are not going, in most of the cases, we're not going to get any connectedness, but we'll see that we'll get results that certain Kähler-type embeddings can be mapped to each other by simp intersection with diff-knot. Symplectomorphisms that are smoothly isotopic to ID. And then at this point, let me also note that Cm omega, the space of Kähler-type complex structures compatible with omega, is by no means diff-knot invariant. Actually, diffeomorphism does not preserve omega. It's diff-knot, it's not simp-knot. Okay? So we'll be looking at the diff-knot orbits of Cm omega, which is not by itself diff-knot invariant. Okay. So that's the another piece of introduction. The final piece of introduction is related to blowups, to complex blowups. So it has been known since the work of McDuff and Pulterovich in the early 90s that studying symplectic embeddings of balls into, say, closed manifolds is closely related to studying whether certain homology classes on the complex blowups of these manifolds can be realized by symplectic form. Okay. And therefore, here in this story, we'll see that as we are going to study Kähler-type embeddings, we are going to ask whether certain homology classes of the blowups can be realized by Kähler forms. Okay. But for this, I need a bit of a bunch of notation. So if I have a k tuple of points of M, right, I'll denote it by as here. Here, X is just the bold X is just a k tuple of points of pairwise different points on M, and M hat K is just the space of all such k tuples of pairwise distinct points of M. Okay, and assume that I have now a complex structure on them, then I can consider the complex blowup of the corresponding complex manifold Mi at the points x1 and up to xk, and this will be denoted by tilde M with the indices I and bold X. So this is the notation for the blow up of M with respect to the complex structure I at the points x1 up to xk. Okay. And the I tilde will be the lift of the complex structure to the blow up. Also by pi, I will denote the natural projection from the blow up to the original manifold. And then E1 up to Ek will be the homology classes Poincare dual to the homology classes of the exceptional divisors. Okay. And then the relevant homology classes of the blowup that have to be studied, or which you have to understand whether they can be realized by Kähler form or not, are the following classes. So you pick real numbers R1 up to Rk. These are the radii of your balls. And then we're going to define the following set. This is the set of all complex structures, Kähler-type integrable complex structures on M that are compatible with omega and such that for some k tuple of points in M, when I blow up with respect to that complex structure at these points, the homology class written here is Kähler with respect to the complex structure of the blow-up. So these are the relevant homology classes for the study of symplectic embeddings of balls. So if you want to study symplectic embeddings, you ask whether such classes can be realized by symplectic forms. And in our case, we would like to know, would like to consider the case when they can be realized by Kähler form. Okay, so again, K of R is just the tuple of this real numbers, R1 up to Rk. K of R is the space of all integrable Kähler-type complex structures on M compatible with omega and such that for certain X, you can blow up your complex manifold and get this homology class is Kähler. Okay. Okay, so now I'm ready to state the first result is just the result about the existence of Kähler-type embeddings in general. So this is good. I'm going to state two general results, and then I'm going to discuss applications to specific manifolds. So the first general result is about existence. So existence of Kähler-type embeddings. Once again, M and omega as before. M is a closed manifold. Omega is a fixed Kähler-type form. And I fix a collection of radii of the balls, R1 up to Rk, and then the following are equivalent. So the existence of a Kähler-type embedding of such a collection of balls into M is equivalent to saying that the set we've just seen is non-empty. So if you want to envelop this definition, it means that there exists a Kähler-type integrable complex structure on M compatible with omega and the tuple of points in M such that for the corresponding complex blow-up, the relevant homology class is Kähler. Okay. In fact, you can say more. So more precisely, if you already have some complex structure on M compatible with omega, then the following are equivalent. So there exists a k tuple of points in M such that the blow-up with respect to that complex structure I and these points for this blow-up, the corresponding homology class is Kähler. And this is equivalent to the existence of a Kähler-type embedding. the balls into M. So Kähler-type embeddings are I Kähler-type for some I. So in principle, you can say more. If you have a particular I and you want if you wonder whether there exists an I Kähler-type embedding, then you have to check that you can find some axis for which this homology class is Kähler. Okay, so that's the existence theorem. Few remarks. The proof is a modification, not really straightforward one, but rather direct if you know what you are doing. Modification of the proof of a similar result for symplectic embeddings of ball due to McDuff and Polydisks for 1994. And as in that work of McDuff and Polydisks, you can actually get a version of this result if you remove a complex subvariety from proper complex submanifold from M. So this allows you to get the existence of Kähler-type embeddings or high Kähler-type embeddings into an open manifold obtained from M by removing a hypersurface. For instance, if you remove from CPN projective hypersurface, you get a ball. So this allows you to get the existence of Kähler-type embeddings into balls.
But this is specific for the second part of the statement, the more precise one. If you remove something that is complex with respect to this I, then
yes. You have to understand with respect to what I this surface, the submanifold is complex, right? Yeah, I agree. Okay, so that was the general existence result. And now this was it's not the main point. So as I said, this is just a modification of the original McDuff and Polydisks result. The main point, which comes from our original motivation, is about the connectedness, or more precisely about the action of groups of symplectomorphisms. So this is the next general result concerning connectedness. So here I start with the following. I pick a connected component of the space of all Kähler-type complex structures. And I assume that when I take the set K of R that we've seen before, intersected with this connected component and projected to the Teichmuller space, the resulting set is connected. So let me recall again what is this K of R intersected with C naught. So it means that I'm considering integrable Kähler-type complex structures on M lying in C naught in this connected component that are compatible with omega and such that for some K tuple of points, I can blow up the resulting complex manifold in this K tuple, and the appropriate homology class will be K. So this is K of R intersection with C naught. And then I project this set to the Teichmuller space. And I want the projection to be connected. So if the intersection itself is connected, of course the projection will be connected, but here I require something weaker. And it's enough. Okay, the projection is connected. Okay, then the claim is that any two Kähler-type embeddings of a collection of balls given by this R, right? Any two Kähler-type embeddings of this collection of balls favoring C naught lie in the same simp intersection with diff naught orbit. In particular, a posteriori, what you get is that both are of I Kähler-type with the same I. This is what you get a posteriori. A priori, you didn't know it. You just knew that they both favor C naught. You knew that you can pick complex structures with respect to which they're holomorphic from the same connected component of CM, but you didn't know that you can pick them up from the same diff naught orbit. Okay. A posteriori, you know that you can. So in addition, if you know more, and in the applications, we'll see that this can be checked. If you know that simp H acts transitively on the set of connected components of CM intersecting CM omega, namely the connected components that contain complex structures compatible with omega, then actually any two Kähler-type embeddings of the same collection of balls lie in the same simp H orbit. You can map any of them into any other by simp H. If you know that simp H acts transitively on the set of such connected components. Okay. So these are general results for manifolds of any dimension. So let me make a few remarks.
Sorry, can you once again say, what does it mean that both embeddings are of I Kähler-type for the same M, for the same I?
It means that you can pick complex structures with respect to which these embeddings are holomorphic and such that these complex structures are compatible with my omega, so that both complex structures lie in the same diff-node orbit. I didn't know it in advance.
And what was the assumption about disconnectedness?
I only knew that I can pick these two complex structures from the same connected component of C of M. I didn't know that I can pick them up from the same orbit, from the same diff-node orbit.
I see. So
a posteriori, I know this.
And orbit is of this simp intersect div zero, right? Orbit of what? Or just div
orbit,
zero?
Or when I'm talking about complex structures, just of div zero. Well, okay, this simp intersection with div zero, even more. Okay, you're right. But in particular, that means that there simp intersection with div zero implies div zero, and that tells me that both complex structures lie in the same diff-node orbit, meaning that they're I Kähler-type for the same. But yes, you're right that in principle we get something more.
Yes, and if in addition simp H acts transitively, so then conclusion is not about complex structures, about something else, right?
Conclusion is that two embeddings can be mapped by simp H into each other. Okay, you can add to this. I didn't write it up, but you can add to this that then both embeddings are holomorphic with respect to complex structures compatible with omega and lying in the same simp H. You're right.
I see. And simp H lies inside simp M omega intersect div zero, of course.
No.
No. Vice versa.
Vice versa, of course. Yes.
So conclusion is, I don't know. So second conclusion is stronger than the
you have an additional condition and an additional conclusion. If in addition simp H acts transitively, then you know more than before.
Okay, I see. Thank you.
Thank you. So, as I said again, this is a general result about all symplectic manifolds admitting Kähler structures. So let me say a few remarks. What happens in the dimension 4? In dimension 4, because of McDuff's result, we know more. Assume we're in dimension 4 and we are in the setting of McDuff's theorem, namely our M is enough non-trivial ground fit invariance, for instance, rational surface. Then for any collection of balls, any two Kähler-type embeddings of this collection, if they exist, can be mapped into each other by simp node. So any two symplectic embeddings of this collection can be mapped into each other by simp node by McDuff. So in particular, any two Kähler-type ones can be mapped into each other by simp node. So in this case, automatically the space of Kähler-type embeddings is connected. Consequently, we get that the space of Kähler-type embeddings is connected as long as it's not empty. Empty space is also connected, actually. And moreover, we know the following. So assume for a particular collection of balls, you know that there exists some Kähler-type embedding of this collection of balls into M as in McDuff's theorem. Then any other symplectic embedding of the same collection of balls will be also of Kähler-type because it lies in the same simp node orbit, and simp node action preserves this Kähler-type property. So these manifolds have the following nice property that as soon as you manage to find one embedding of a particular collection of balls, which is Kähler-type, all embeddings of the same collection of balls will be of Kähler-type. Okay. So if you are going to look for symplectic embeddings that are not of Kähler-type, you better not to look there. There you have no chance. Okay. So I'm done with the general results, and now I'm going to discuss applications to specific manifolds. And as I said, these are the manifolds where we know something about the corresponding Technion space based on the work of previously done by complex geometers. So if there are questions about the previous part, it's a good time to ask them here. Okay, so let me move on. So let me start with the applications to the case of CPN. First, I'm going to discuss existence. Okay. And as I said, in the case of CPN, what's good about CPN that we know quite a lot about the Technion space in this case, and this is due to the classical work of Hirzebruch, Kadeira, Yao, Fröhlicher, and Neinhaus. Someone already did this job for us. So the theorem is the following. So in the following cases, we have necessary and sufficient conditions for the existence of Kähler-type embeddings of a collection of balls into CPN equipped with the standard Fubini-Studi form. So omega Fs is the standard Fubini-Studi form. And these are the cases that actually also appear in Magda-Poltorovich's paper for symplectic embeddings. So where something is known as symplectic embeddings, which is no miracle because in that paper they also use the description of the Kähler cones. They realize they check when appropriate homology class on the blowup can be realized by Kähler forms, not just symplectic. So it's no wonder that we get more or less the same result, but we strengthen the result by getting Kähler-type embeddings in the same cases. Okay, so these are the two cases. One case is when you have L to the N equal balls. L is just an arbitrary natural number, and N is the dimension of CPN. Okay, and that's one case. The other case is we're going to consider embeddings of up to 8 possibly different balls into CP2. So in these cases, the only restrictions, so in the first case, the only restriction is the volume. In the second case, the restrictions for the Kähler-type embeddings, the equivalent conditions for the existence of Kähler-type embeddings are the volume condition plus additional explicit quadratic inequalities on the right, coming from the description of the Kähler cone of the blowup of CP2AK generic points. K is from 1 to 8. Okay, and these are the conditions that already appear in McDuff and Poltorovich's paper. In particular, so in both cases, for any complex structure I on CPN compatible with the symplectic form, and in particular for the standard complex structure, there exists an I-Kähler-type embedding of the balls into CPN. So before we are talking about Kähler-type embeddings, now we want to be more specific. We're talking about I-Kähler-type embeddings, and here you'll get I-Kähler-type for any I compatible with omega Fs. But note that in principle, such an I for n3 and higher, such an I does not have to be smoothly isotopic to standard complex structure. For complex projective spaces of dimension higher, complex dimension higher than 2, there may exist complex structures, Kähler-type complex structures that are not isotopic to the standard in principle. And of course, as I mentioned, for symplectic embeddings of such collections of balls into CPN, this result was proved in McDuff. Okay, so that was the existence of Kähler-type embeddings of balls into CPN. Now, here's one particularly nice corollary of this. So consider the standard complex structure in CPN and assume you have a ball of volume less than CPN, on the volume of CPN. Then you can find a Kähler form omega on this complex manifold isotopic to the standard Fubini-Studi form, and such that the resulting Kähler manifold admits a Kähler that's both holomorphic and symplectic embedding of the ball with a standard flat Kähler metric on it. So basically it means that if you look at CPN with the standard complex structures, you can always pick a Kähler form such that the resulting Kähler metric is flat on an arbitrarily large part of your manifold, volume-wise. So it means that you can actually pick your Kähler form so that the whole curvature is squeezed into a very tiny part of your manifold. Away from that part, your Kähler metric is not just flat, it's just standard. So you have a standard flat ball sitting in there. Okay. And actually for n equal to 2, this was previously proved by Eckel. Okay, a few more remarks. So in the case of CP2, actually, any complex structure in CP2 compatible with the standard symplectic form is smoothly isotopic to the standard one. So previously I said that for CP6 and higher, you may have exotic ones. Here, all complex structures compatible with the symplectic form all have to be isotopic to the standard one, and this follows. Probably there are simpler ways to get it, but it easily follows from the combination of difficult theorems of Yao, Froelich, and Neuenhaus, and Gromov. Gromov about the topology type of the group of symplectomorphisms of CP2. That's one remark. And the other remark is that in the cases that we discussed above about the existence theorem for CP2, when we have a square number of equal balls or up to 8 possibly different balls, then any symplectic embedding of such a collection of balls into CP2 is of Kähler type. Because as soon as you have one such embedding, as I said, all of them are of Kähler type in this case. Yeah. And that's what you get by using McDuff. Okay. Now let me discuss the connectedness result for CPN. I have two general results about Kähler-type embeddings of balls, existence and connectedness, and in each application we're going to discuss existence in that application and connectedness in that application. Okay, so connectedness in the case of CPN. So for any collection of radii, any two Kähler-type embeddings of balls into CPN with a standard symplectic form can be mapped to each other by simp, which in this case is simp H. In this case, simp and simp H are the same, and they can be mapped. These two embeddings can be mapped into each other by simp intersection with diff not if and only if they favor the same connected component of the space of Kähler-type complex structures in CPN. But this is something we do not know in general. If you give me two Kähler-type embeddings, how do I know that whether they favor the same connected component or not? That's the complication of the picture. So that's as good as we can get. Let me make a few remarks now about this claim. So for n equal to 2, as we already seen, the situation is much nicer. So the group simp intersection with diff not in this case is just simp not, because simp is connected in this case by Gromov. And this means that for any collection of balls, the space of Kähler-type embeddings of this collection to CP2 is actually path connected. They all lie in the same simp not orbit. But of course, we could have got it from the very beginning from McDuff's result without using our theorem. So at this point, our theorem yields the same corollary as McDuff. So if you look at the case of CP2. Okay. Now, in higher dimensions, life can be more complicated. For CP6 and for CP8, it's known that the space of Kähler-type complex structure in CPN actually has more than one connected component. Well, it doesn't tell us on the spot that there will be Kähler-type embeddings favoring these exotic connected components, but who knows? Maybe there. And for other n, it's actually unknown. For CP10, it's not known whether C of CPN has more than one connected component. Also, let me remark that for n greater than 2, it's unknown whether the group of symplectomorphisms is connected or it lies in diff not. Do there exist exotic symplectomorphisms of a CPN in for n higher than 2, it's a no. Okay, so much for the application to CPN. Are there any questions? Okay, then I'm going to move to the applications to the case of Tori and K3 surfaces. So I assume now that my M is either a torus or a smooth manifold underlying the K3 surface. So in standard terminology, K3 surface is already a complex surface. So what I'm talking here about is a smooth manifold underlying that complex surface. And it's known that all K3 surfaces are diffeomorphic. So basically, we're talking about a very specific smooth manifold. And assume that omega is a Kähler-type symplectic form on M. Okay. So in these cases, also, we're going to use the information about the type mirror space of the Kähler-type complex structures on M. And this information was obtained for us by previous generations of complex geometry. Let me just make a few remarks that how should one think of Kähler-type symplectic or complex structures on Tori compatible with the standard orientation? These are exactly the ones that can be mapped by diffeomorphism of the torus to a linear complex or symplectic structure. So linear complex structures are the ones that come from R to N. My T to N is the quotient space of R to N, and I can consider complex structures, symplectic structures that actually come from R to N, from the linear complex or symplectic structures in R to N, and these are called linear symplectic or complex structures on Tori. And Kähler-type is equivalent to being diffeomorphic to linear. Okay? And for Tori of dimension 4 and higher, it's unknown whether there exists a non-Kähler-type symplectic form. Also for a K3 surface, it's unknown. It's unknown whether all symplectic forms are of Kähler-type. And for complex structures, actually, Tori of dimension of real dimension 6 and higher may have non-Kähler type complex structures. And that's the result due to some Meze, Borisov, Simon, Salomon, and Vetzlovsky. And for K3 surfaceization is nicer due to classical theorem of Siu from 83, if I'm not mistaken, that any complex structure on K3 is actually of Kähler type, and moreover, its first Chern class is 0. So that's the complex structure that you want to get K3. So for K3 surfaces, there are no exotic complex structures, but for Tori, there are. Okay, but we are dealing only with Kähler type complex structures. These exotic ones are just, I mentioned them for fun. Okay. The result that C1 of that complex structure on K3 is 0 is due to Baville, not to Siu. Siu proved that any complex structure is Kähler type, but Baville noted then that it is automatically as C1 equal to 0. Okay, and one more definition concerning Tori and K3 surfaces is that the form omega, the symplectic form, Kähler type symplectic form omega on M is called rational if its homology class is proportional to rational. Proportional meaning a real multiple. And it's called irrational otherwise. And there'll be an important difference between rational classes and irrational, rational forms and irrational. Okay, so what can we say about the existence of Kähler-type embeddings for Tori and K3 surfaces? So assume my M is either an even dimensional torus or a K3 surface, and assume I have a Kähler-type symplectic form, and I assume that either this Kähler-type symplectic form is irrational, or we are in the very elementary case when my M is just a dimensional torus. Then there are no obstructions for Kähler-type embeddings other than the volume. So I have what's called unobstructed symplectic embeddings. The only obstruction is the trivial one, the volume. Otherwise, there are no obstructions. So sometimes in such situation, we say that embeddings are unobstructed. So Kähler-type embeddings of balls into Tori and the K3 surfaces are unobstructed. For symplectic embeddings, this was first proof for T4 and K3 by Latchev, McDowell, Schlenk. This for almost all symplectic forms of T4. And in the full generality for all symplectic forms in all dimensions, this was proved, even for rational symplectic forms, was proved in our work with Verbitsky from 2016. Remark there, actually for the torus in just one ellipsoid, not ball, but just one ellipsoid, in particular for one ball, this was recently proved by Loof and Wang using a similar method. And funnily enough, their work is relates this problem for tori to Gabor frames, which is an important notion in signal processing. The very intriguing connection related to arithmetics of lattices defining complex tori. So that's the remark that I wanted to make. So much for the existence of Kähler-type embeddings in Tori and K3 surfaces. Now let me move to the connectedness part. So again, I assume I have a Kähler-type symplectic form M, and I assume that either omega is irrational or I'm just in a very elementary two-dimensional case. Then any two symplectic embeddings, any two Kähler-type embeddings of the same collection of balls into M can be mapped into each other by simp H, by the Tarelli group. And they can be mapped into each other by simp intersection with if not, if and only if they favor the same connected component of C of M. And again, here I have no idea how many connected components are there. Well, except for the case of T2, and the station is trivial anyway. Okay, a few remarks now. It's a well-known open problem. It's listed as an open problem in McDuff and Salmon book, is whether simp H is actually equal to simp not for tori, and greater for higher dimensional tori, for T4 and higher. Is it true that any symplectomorphism acting trivial on homology is actually symplectic isotopic to identity? That's a well-known difficult open problem. So a priori, we can't say anything. So it shows that life may be as complicated in principle as appearing in the theory. So simp H might be in principle different from simp intersection with diff not. For K3, for the K3 case, it's known to happen. In the K3 case, for at least some irrational omegas, it's known that simp not is not equal to simp H. That's due to Sheridan and Smith. And it's known also for possibly some other rational omega that simp not is not does not lie in simp intersection with diff not. So it lies sort of. It's known that it lies there, but not equal to. Sorry, it's known that simp not is just not the intersection of simp with diff not. There might be symplectomorphisms that are smoothly isotopic, but not symplectic isotopic. And this is due to Zeider, and who showed that this is true for some symplectic forms on K3, and Smirnov recently verified that for lots of irrational symplectic forms, this is definitely true. Okay. So this means that there is a chance that the space of Kähler-type embeddings favoring the same connected component for the case of Tori and K3 surface is actually not connected. So even there, we don't get connected. There's also a chance that there might be Kähler-type embeddings which favor different connected components of C of A. But again, we don't know. Okay, but what else can we say in the case of Tori? Actually, in the case of Tori, if the form is rational, the station is different. Then there may be obstructions to the existence of Kähler-type embeddings of balls into M that are independent of the symplectic volume. So there might be more restrictions. And for instance, there might be obstructions coming from Shadr constants. So here's an example. So consider T4 with the standard Darboux form. So the volume in this case is 2. And then for any complex structure ion C4 compatible with omega, one can biholomorphically identify the corresponding complex manifold with what is called the principally polarized abelian variety. And for such complex surfaces, there is a universal bound on the Shadr constant. Shadr constant is purely complex notion. So for such complex manifolds, there is a universal upper bound in Shadr constants due to Stephans, and it yields that bounded Chandra constants translates into a bound on the maximal possible volume of a ball that can be Kähler-type embedded into this symplectic manifold. And this yields that if the volume is between 4/3 and 2, then there are no Kähler-type embeddings. Okay? But we know that for symplectic embeddings, there are no restrictions other than volume. So for such R, there do exist symplectic embeddings of a ball. This is first was proved by Latchev, McDuff, Schlenk. And so this way you get that any symplectic embedding of a ball of a volume between 4/3 and 2 is definitely not of a Kähler-type. We get symplectic non-Kähler-type embeddings. So the summary is that for irrational forms on Tori, there are no obstructions other than the volume. For rational forms, there may be obstructions in addition to the volume. And the question is, let's look at rational forms. Can we do better than just showing the existence of symplectic embeddings? The existence of symplectic embeddings is known for rational or irrational forms, as I said, due to Latchev, McDuff, and Schlenk now work with Verbitsky. So the question is, can we do better? For instance, can we relax a bit the notion of Kähler-type embedding, say that it will be almost Kähler-type in a certain sense, so that, again, the only restriction will be the volume. So the answer is that there's a good answer and the bad answer. The good answer is that we can do it, and we'll show that for all irrational and majority of rational forms, such almost Kähler-type embeddings are unobstructed. There are no obstructions under the volume. The bad news is that we cannot say, if you give me a particular rational form, I cannot say whether it belongs to this majority or not. So for instance, for this specific Darboux form on T4, I cannot say whether it's in there or not. So let me now say what are these almost Kähler-type embeddings. These are called Tame embeddings. So we're in the following situation. So assume we have a closed manifold. Definition is general. M doesn't have to be a torus or a K3 surface. So M is a closed manifold. Omega is a Kähler-type symplectic form in it. Ball W is a disjoint union of compact domains with boundary in R to N. And as we'll see in applications here, we also allow these domains to be not only balls, but also polydisks and parallelepipeds, this kind of things. And then we fix epsilon greater than 0, and we consider a symplectic embedding of these domains, collection of domains into M omega, and we say that this embedding, the symplectic embedding is Epsilon-tame if it is holomorphic with respect to some, again, not a priori fixed Kähler-type complex structure, I on M, which is epsilon almost compatible with omega, in this, I would say, in the sense of Hodge theory, say. Not all conditions come from Hodge theory, but some do. So you can think about it as epsilon almost compatible in the sense of Hodge theory. And the conditions are the following. So first, it has to be tamed by omega. Of course, if my complex structure is compatible with omega, it is particularly tamed by omega. If I perturb my compatible complex structure a bit, again, I'll get a tamed complex structure. The second condition is that the homology class, the one part of the corresponding homology class of omega, has to be Kähler. And this is a really non-trivial fact that if you start with an integrable complex structure, you start with a complex structure compatible with omega and you perturb it a bit, then this property is still true. So if I is compatible with omega, then omega 1,1i is just a homology class of omega. Of course, it is Kähler. But if you perturb by a bit, why does this class have to be Kähler? It's a classical, very difficult theorem of Kader and Spencer, called Kader-Spencer stability. So for I close to compatible ones, this will be still true. And the other condition is that the 2, 0 plus 0, 2 part of this homology class has to be L2 small. It has to be smaller, epsilon smaller in the integral metric. And these are the conditions that have to be satisfied. Of course, if you, for the last condition, if you perturb I a bit, if you started with an I which was compatible with omega, of course, this 2, 0 and 0, 2 parts will be just 0. But if you perturb it a bit, this Hodge decomposition changes continuously, and of course you'll get less than epsilon as long as I is close enough to an integrable complex structure. Okay, and let me add here that in principle I could have added here more conditions, but for the results that will follow, I can add here more conditions to this definition. What I need from this condition is that it should be these conditions you see, these conditions depend on omega, and they should be open with respect to I. They should contain the complex structures compatible with omega. And when I act on omega by diffeomorphisms, this condition should change appropriately. The condition is dependent on omega, so when I change by diffeomorphism my omega to omega prime, the omega condition should change to the omega prime condition. So these three conditions, of course, satisfy these properties, but I don't know any other nice conditions with this property, so I didn't list them. In principle, if you know some, tell me. We can just add it to the definition. Okay, and the immediate remark is, of course, that for being Kähler-type automatically implies Epsilon-tame for every epsilon. And compatible I, of course, is tamed by omega. For a compatible I, the one part of the cohomology class is omega itself. The cohomology class of omega itself, it, of course, is scalar. And the third condition is also trivially satisfied. So we are getting indeed a relaxation of the notion of Kähler-type embeddings. Okay, and for this epsilon-tame embeddings, we can state the following existence result. So I assume that my M is either a torus, an even-dimensional torus, or a smooth manifold deriving K3 surface, and my collection of domains is this joint union of complex domains with boundary, which will be specified in the next slide. So let me postpone for which W this is true to the next slide, and let me state first what is true. And for any epsilon, I can find an open, dense, and diff plus invariant set of Kähler-type symplectic forms on M, depending on these domains on epsilon, and containing in particular all rational Kähler-type symplectic forms on M, so that for each omega in this open and dense set, the embeddings, the Kähler-type embedding, the epsilon-tame embeddings of W into M are the only abstraction is symplectic form. Okay. So this is an open dense subset in the space of symplectic forms, and actually contains all rational forms in small over diff plus invariant. So it's a huge subset of the space of all Kähler-type symplectic forms. For all of them, we have no restrictions on epsilon-tame embeddings other than the wave. Okay, and for which W does it hold? This holds at least if W is either of the following. So it is joint union of K two-dimensional balls. This was the setting of our previous theorems. It is joint union of K identical copies of parallelepiped. Parallelepiped is just to pick a basis of R2N and span the unit parallelepiped using this basis. That's what's written here. And in the torus case, you can also let W to be this joint union of K identical copies of a polydisk. Polydisk is the symplectic direct product of balls, and here the number of balls is L, and the cell can be arbitrary. Okay, so that's the existing result. And the remark is that for the torus case, for all W above and all epsilon, this open dense subset in the space of all Kähler-type symplectic forms that appears in the theorem, it actually contains a diff. Okay, so it's a type of diff plus T2N orbit of an irrational Kähler-type form. Okay, so you don't not only get an open dense set. This open dense set contains actually a certain dense orbit, diff plus dense orbit of an irrational form. Okay, and for what you can say more here, that for each irrational form in that diff plus dense orbit, you not only have an epsilon-tame symplectic embeddings that are unobstructed, you also have a Kähler-type and abstracted embeddings of these domains. So for instance, for any such irrational form, you have unobstructed Kähler-type embeddings of parallelepipeds or polydisks. Okay, so this is it. Sorry for going over time. Thank you very much.
Thank you very much. Are there any questions?
I see here some questions in the chat, so let me. Yeah, so that's what I answered here, that for the existence of Kähler-type embeddings, if you remove, for the existence of, say, I Kähler-type embeddings, it's okay to remove proper complex hypersurface with respect to I.
So I have a question. So I know that there are some, in the case of symplectic embeddings, there are some works by I think Biran and Hopstein about full packings or about being able to isotope. So do you think it can adapt to your settings, or?
I don't know. Our techniques certainly do not allow to produce full packings, very full packings. The packings that fill out the whole volume, not up to Epsilon. I don't know. It may be possible, but it certainly requires more work.
So some of their work is based on the Biran decomposition of the manifold. You know, not sure how it's called, but with the Donaldson hypersurface and so on.
Yes.
And so I guess that this kind of thing exists also in the Kähler-type, so in the Kähler situation. So I don't know. Just
I don't know.
Okay.
Misha, did I understand correctly? Then there is a huge difference between Epsilon-tame and compatible, in what that for Epsilon-tame you can kind of full indefinitely until volume permits, right? And with compatible, in the case of torus, you have these abstractions coming from Syshadri constant.
Right. So for tori, saying for rational forms on tori and balls, Epsilon-tame embeddings are unabstracted for most of the rational forms. For most of the rational forms, Epsilon-tame embeddings are unabstracted, but for some rational forms, Kähler-type embeddings are abstract. But the problem is that I cannot match these two cases. So I cannot say my techniques and our techniques are unfortunately not that good. So,
but it would be cool to match them, right? So because this is a kind of fantastic rigidity result.
We spend a lot of time.
I see. I have another question. So concerning this work by Eckel, which you mentioned, right? So, where he built this kind of flat Kähler structures with huge flat pieces, right? So I think he was motivated by, so to say, Nagata conjecture, right? So basically, I don't know, I maybe missed if you mentioned this. So there is some kind of tension between Kähler packing and symplectic packing for CP2. Because kind of this Biran packing by 10 and bigger balls.
Of course.
Are not known to be Kähler, and the abstraction is exactly this famous conjecture by Nagata, which goes to his work on Hilbert's problem.
Of course. So I didn't say anything about Kähler-type embeddings of more than 9 balls into CPU2. And why can't I say anything there? Because I don't know basically anything about Kähler cone of the blow up of CP2 at generic 10 points. So, and describing such a Kähler cone is, of course, a problem that includes in particular Nagata conjecture, because Nagata conjecture says that Nagata conjecture is equivalent to saying that a certain homology class lies in the boundary, a certain particular class lies in the boundary of the Kähler cone. So if you know the description of the whole Kähler cone, then of course you get the Nagata conjecture. But even Nagata conjecture is very difficult. So getting more information about Kähler cone is
maybe a kind of extra advertisement for the definition of embedding of Kähler-type, because in some cases, so this is just major open problem in algebraic geometry.
Yes. So if for blow-ups of CP2 at more than 9 generic points, one will be able to show that symplectic cone is different from the Kähler one, then of course you'll get examples of symplectic and non-Kähler type embeddings of both.
So there is another question.
I'm sorry. You see?
Wow.
Okay. Well, this is not a question, but rather a statement. Okay.
More questions? Okay.
So, for example, sorry, in the say in the nice torus case, when embeddings are unobstructed, can you say anything about, let's say I have my favorite standard complex structure. Can you say anything about when there's an example that when there's an embedding that favors its class?
Sort of the standard so the complex structures that are good for on Tor are the ones that do not admit any complex subvarieties. That's simple complex structures. So as soon as you have an irrational symplectic form, it is compatible with such a complex structure. And then you are in very good shape. Then you know that you do have I Kähler-type embeddings for this I, which is component. But the standard complex structure, or say the standard one coming from CN is not component.
I see.
For that, I'm not sure. I can say something. But component simple structures are generic, so you just perturb a bit your favorite complex structure, and you get component simple.
Thank you.
Other question?
Well, I have a question. So you mentioned this work by Louis and Wang, where
Yes.
they considered.
Thank you for pointing out this work to us. It was were you who pointed it to us. Okay.
I already forgot. But I mean, for torus, they were able to say something about ellipsoids. And can you say about now? I mean, this is a fancy subject due to work by Magda von Schlegel, embed ellipsoids. So can you, in which situations you can extend your work with Verbitsky to the case of ellipsoids?
So this is the project which we Student of mine has been thinking about. I believe that the existence results should hold for ellipsoids as well. So we should be able to generalize this Loof and Wang for any connection of ellipsoids for Tori and K3 service. Because for balls we already did it with Verbitsky in previous work several years ago, and I think that the same ideas should lead to the existence result here. For the connectedness, probably also true, but I'm not quite sure at this stage.
Okay, so maybe it's time to thank Misha again. Thank you very much.
Thank you very much. Thank you.